Hi everyone, my name is Elliot McDonald, and today I'll be walking you through AMPL Tutorial 1. Machine learning models are capable of some impressive prediction, but just like I can't eat an unpeeled banana, machine learning models can't eat unprepared data. Instead, we curate the data in order to ensure that the chemical structures and properties are represented consistently. First, we're going to do an overview of how this curation process works, and then we're going to open up the code and do it ourselves. AMPL provides 5 custom functions to make cleaning your chemical data as easy as possible. Let's take an example here where we have our raw uncurated data comprised of chemical structures called smiles. We have relations which tell us the true value was less than or greater than the value given. We have some value for us to predict, in this case the inhibition constant Ki, and then we have the units for these values. For example, we see in the second to last row, we have CC1, CN, CN. The inhibition constant is some value that is under the highest value that they tested, which was 0.2 nanomolar. Our goal in this curation process is to standardize all of these values in this table as much as possible to make the model's job in predicting the Ki values from the smiles fairly straightforward. First, we're going to employ our first function, base smiles from smiles, which will allow us to take smiles from our chemical database and remove possible salt groups or isotopes from the string, so we're just left with the base, ignoring the extra details. In this specific example, we remove the sodium salt group and the isotope number on the chlorine. Next, we're going to use compute negative log response. This will allow us to turn the KIs into PKIs, which help to stabilize the variation in the data in order to help the model more accurately find the trends. And in this process of computing the negative log, we also need to invert the comparison operator. Since, for example, if the Ki for CCO-Cl is greater than 5e-7, then the negative log of its Ki is less than the negative log of 5e-7. In this step, we're also going to make sure that we are converting all our Ki's based on one unit, so based on molar, and not based on the unit that it's given, like nanomolar or micromolar. Next, we're going to utilize the function standardized relations. You may have noticed that some of the relations in this table have quotation marks around them for no reason. And in the case of our last two examples with comparison operators, we note that a greater than sign means the same thing as a greater than or equal to sign in this case. And so both with the quotation marks and with the equal sign next to the relation, we can get rid of them and get them all into one form. As with any data set, there are always outliers that have to be removed. And so to address this, we employ remove outlier replicates, which identifies any compounds in the data set that have multiple entries. And if they do, it ensures that if there are any outliers, they are removed from this data set. In this case, look at the PKI of 1.505. It is drastically different than the other replicates in its group, and thus we will kick it out of our data set. Lastly, we're going to use aggregate assay data to combine those replicates that remained into one value using averages or maximum likelihood function for those with comparison operators. And finally, we are left with our final curated data that we can start working with our model on. Let's get a deeper look at each of these steps by going to visit the code. The first step we will do is import the basic libraries that we're going to use in this tutorial: OS, Pandas, NumPy, Matplotlib, and Seaborn. Once we've imported each of those, we can read in our data from the CSV that it was given in and convert it into a Pandas data frame. We can check the shape on the data frame in order to find that the data set is comprised of 2,236 rows and 6 columns. Raw df columns values gives us a list of each of the names of these columns. We've seen 4 of the 6 of these before, but we also note that molecule Chembl ID, which we didn't have in the table, is an identification number that's used in the Chembl database. And standard type specifies the type of measurement that we're looking for. In this case, the inhibition constants again, Ki. Now we can start running our data cleaning methods. We start with base smiles from smiles to remove those salt groups and isotopes and just get the base smile string that we want. After importing the function, we run it by inputting the smiles column as a list and assigning it to a new column in the data frame as base rdkit smiles. Note that we also specified a number of threads called workers to help accelerate the speed of the function. Looking at the number of unique entries in both the original smile strings and these new base miles shows that we, in fact, did succeed in simplifying some of those miles because we see that there are less. Next, we're going to call compute negative log response. Our data spans across many orders of magnitude, which makes it difficult for a machine learning model to handle variances which change significantly with the magnitude of Ki. So this pKi is going to make for a more accurate model. After importing the function, we call it on our data frame, specifying the columns that each of the units are in, the columns that we want added with the new pKi values, the columns with the relations, the unit string meanings for our unit conversion purpose, and an in-place parameter that just specifies whether or not we want the change to be in the inputted data frame or as an output of the function. We can then graph the original Ki and pKi as histograms to see their distribution. As you see in our examples from earlier, sometimes databases have different formatting when it comes to relations. Some databases can have less than or equal to signs, when others just have a less than sign. And some databases can leave the relation column empty to mean the same thing as an equal sign. We call the standard relations function that we talked about earlier to make all of the relations format the same way. The parameters that we pass in include our data frame that we're using, the name of the old relation column, the name of the new column that we want our corrected relations to be put in. You may notice that we also name the chemical database that we are using under the DB parameter to help the function apply database-specific formatting changes. By looking at the counts of each type of relation in the old and the new column, we can see that we successfully standardized many of them. At this point, we have standardized the smiles, standardized the units, converted the Ki to pKi, and standardized the relations. All that's left is the data creation process for our last two functions to deal with any chemical structures that have multiple values in the database. Our first function is remove outlier replicates, which will take in our data frame the column with the chemical IDs, the response column, and the max difference threshold. The threshold is the maximum difference that we are going to allow a pKi value to be from the median of all the other pKis listed for that chemical before we decide it's an outlier and removed from the list. We run this function and assign our output to a new data frame called curated df. Once we move all of our outliers, aggregate assay data will combine all the multiple values listed that we didn't decide were outliers. Since this is the last step in our creation process, this function has us input all of the relevant columns from our data frame, and that way it'll output a data frame with only the core columns that we need. The chemical ID, the smile strings, the relation, and the average pKi for that value. This aggregate assay data has a lot of parameters, so I'll go through each one quickly. The first parameter is the input data frame that we got from remove outliers replicates. The value col is the column for our pKi values. The output value col is the name that we want to assign to the column in the final data frame with the average values. The ID column, smiles column, and relation column are their respective column names in the data frame. Label actives is a parameter that we can use to add a new column with a true-false value, denoting if the compound is active based on the average pKi value. We can use that parameter for classification machine learning models, but we'll ignore that for now for these tutorials. Verbose just asked us whether or not the function should tell us what it's doing as it's working. We can then print the original data shape and the curated data shape to see that we've not only significantly reduced the number of data values since our rows have reduced by several hundred, we've also reduced the number of columns in this last step to just the few columns that our machine learning model really cares about. Finally, we can save our progress by saving the curated dataset that we've made to a CSV file, and that way it's all ready for tutorial 2, when we will split up our dataset into validation and training sets. See you all in tutorial 2.